Hey guys, have your notes pulled up for section 2-3, day 1. And oh my goodness, this is one of my favorite sections in pre-cal. I like polynomials. Polynomials are probably my favorite function. And I say that because in calculus, we deal with so many more difficult functions than just a polynomial. So I like them. I know a lot about them, and I can visualize them very clearly. So that's what I'm going to help you with, is to kind of know what each of these polynomials, how to figure out what they look like on a graph without going to the trouble to like plot all these points. You can just get a nice visual representation of a general representation of what it looks like. Now, I say that because I am a very visual person. So I often look at something and an image pops into my head to go along with it. For example, I'm kind of old school. I grew up learning time on an analog clock. I had this little toy. I loved it. It's a cool little toy. And it helped me learn how to tell time. So then it was probably kind of during my time that all these digital clocks came out when I was just a kid. And I didn't like the digital clocks. I like the analog clock. I like to see where the minute hand is in relation to the next hour or the previous hour. So, honest to goodness, when I look at the time on a digital clock or on my digital watch, Fitbit or whatever, I picture it on an analog clock. Weird, I know. But anyway, I'm going to show you enough about polynomials so that when you just catch a glimpse of an equation that's a polynomial, you'll kind of just know what the graph of it looks like. So, first of all, what is a polynomial? Well, a polynomial, the graph of a polynomial has to be smooth and continuous. No breaks, no jumps, no sharp corners. So quadratics, cubics, quartics, all those. Smooth, continuous. No breaks, no sharp corners. This is an example of something that is not a polynomial because as I'm tracing it, I have to jump from one piece to another. It's not continuous. This one's continuous. I can trace the whole thing without lifting my pencil, but it's got sharp corners in it. It's not smooth. It's got two sharp corners. More than likely, it's a function where the exponents are fractions. More than likely. Now, here's where I get to like drill in some vocab with you. And I've gone through the entire notes. Every time the notes talk about x-intercepts, I'm highlighting those yellow. So, just to review, there are like 4 words that all mean the same thing involving x-intercepts. Okay, so one is x-intercept. The other thing we can call x-intercept is a root, a solution, and a zero. I'm not saying the x-intercept is 0. I'm saying whatever the intercept is, it's a zero of the function. It's an x-intercept of the function. X-intercept, roots, solutions, and zeros. Whatever your x-intercept is, let's call it A. Whatever your root is, let's call it A. Then x minus that number is a factor of my polynomial. Factors, roots, x-intercepts. So, come over here. I've given you 2 quadratic equations that are extremely straightforward. Here's the quadratic equation, it equals y. If I'm trying to find x-intercepts, I'm going to sub in 0 for y, and I'm going to factor it. These are called factors. And to solve this factor, x would have to be -4. To solve this factor for 0, x would have to be +2. These are x-intercepts, roots, solutions zeros. There are two of them. Does that make sense for a quadratic? Yeah, surely. A parabola can cross the x-axis in two places. Of course it can. Here's another one. Here's a quadratic, okay? It's set equal to y. It's a full-on parabola. If you would like to find the x-intercept, you're going to sub in 0 for y, and you're going to factor it. Well, hey, look, these factors are the same. If I solve this factor to be 0, x would have to be negative 3, x would have to be negative 3. Now I get only one x-intercept. How is that possible? For a parabola to only cross the x-axis once. Well, it must be sitting on it. It must be sitting on the axis. The vertex is on the x-axis. So, having said that, let's talk multiplicity. Multiplicity is about how many times a factor or a zero occurs. A factor or a zero occurs. How many times do you see this factor in its factorization? One time. How many times do you see this factor in its factorization? One time. So this factor or this zero has a multiplicity of 1. This factor, or this 0, has a multiplicity of 1. Make sense? How about these? This factor occurs twice. This 0, I didn't write it twice, but it occurs twice, right? So this one has a multiplicity of 2. This root, this solution, has a multiplicity of 2. It occurs twice. What does that mean for the graph? Well, if a 0, or a factor, has a multiplicity that's even, your graph only sits on, it only touches the x-axis. Touches. If your multiplicity is even, your graph touches or sits on the x-axis. If your multiplicity, this one happens once, this one happens once. If your multiplicity is odd, your graph actually crosses through the x-axis. Passes through it. That would make sense, right? Like, can you picture this? This parabola crosses the x-axis at negative 4 and positive 2. That means the vertex is like down there somewhere, and it's opening up, and it's going to cross at this negative value, and it's going to cross at this positive value, and it's going to keep on going. Arrows on top. This one only has one x-intercept, and it's at negative 3. So this parabola is just sitting on the x-axis at negative 3. Where does it go from there? Well, that's positive. So it's sitting on the x-axis and it's opening up. So that's something that you're going to have to memorize, and I just explained all that. Here are the words. If your multiplicity is odd, it crosses, like this one. If your multiplicity is even, it only touches or sits on, like this one. Okay, let's put it all together. I went with the same colors. Yellow for zeros, pink for factors, blue for multiplicity. Check out this polynomial. I've got this binomial occurs once, this binomial occurs 4 times, and this one 3 times. So I don't think you would want to do this, but if you multiplied out this polynomial, you would have to take this binomial times itself 4 times. Take out that huge answer, multiply it by this one 3 times, and multiply it by this one once. What you would end up getting is some gigantic polynomial And the degree would be, well, x times 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 x. Did you get that? X times 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 x. I think it would be an 8-degree polynomial. Whew. Anyway, all right, so these are factors. This factor produces this as a solution, this as a solution, this as a solution. And this 0 has a multiplicity of 1. You know how I know that? Because the factor only occurred once. This 0 has a multiplicity of 4. You know how I know that? The factor occurred 4 times. This 0 has a multiplicity of 3 because the factor occurred 3 times. So here's what this means. When the multiplicity is odd, so like here and here, the graph is going to cross the x-axis. Check this out. Positive 1, see how it passes through? Negative 2. See how it passes through? Multiplicity is even. Kind of hard to see. This is a screenshot of a graphing calculator, and you know that those can be kind of jerky. But what you should be seeing here is it's just sitting right there on positive 3 and heading back up. So it just touches there. So keep that in mind. Multiplicity. And honestly, you know what? I don't have my multiplicity memorized. So while I'm up here teaching, I do not have multiplicity memorized. I know what this graph looks like, kind of, and I know what this graph looks like. So I just think it through. If it occurs twice, I have one x-intercept, it sits on it. If each one occurs only once, it passes through. Once passes through, twice sits on it. That's how I've got my multiplicity memorized. And then moving on, we've got leading coefficients and turning points. So we're going to look at end behavior of your coefficient. So we're going to look at the degree of the polynomial and the leading coefficient. If your degree, let's do this one first. You're so familiar with quadratics. If your degree is even, let's say you have a quadratic, okay? Your degree is 2. What happens when your leading coefficient is positive? You know what happens. Your parabola opens up. What happens if your leading coefficient is negative? Your parabola opens down. You knew that already. Okay, how about a 4th degree? How about a quartic? Same deal. What if your leading coefficient of your quartic is positive? Well, it's going to have like a W-ish look, but both ends are going to point up. What about if your leading coefficient is negative on your quartic? Well, now it's going to look like an M, sort of, but both ends are going to be pointing down. Okay? Craziness might be happening here in between them, but the end direction is going to be like this. Now, by the way, over here. Now let's get a little harder, kind of what a quartic might look like with a positive leading coefficient. Now let's check out a cubic. You all know what a cubic looks like. Sometimes it's really, I don't know, humpy. And sometimes it's not so humpy. But if the degree is odd, like a cubic, what if your leading coefficient is positive? Well, then the cubic, it's going to go down on the left and up on the right. Down on the left, up on the right. But if your leading coefficient is negative, it's going to be backwards. Now it's going to be up on the left side, down on the right side. So a couple of questions here about end behavior. Got this function. It's a 6th degree polynomial. So it's going to fall in this even degree category. And my leading coefficient right there, my leading coefficient is negative. That means each end is going to be like this. Craziness is going to be happening here in the middle, but each end points down. Next one is a cubic. The degree is 3. The leading coefficient right there is positive. This is what my end behavior is going to look like. Okay. Graphs, when you graph your function, whatever the degree is, you're only going to have one y-intercept. It's not going to cross the y-axis and then go back and cross it again. No, it would fail the vertical line test if it did that. So you're only going to have one y-intercept, but it can cross the x-axis as many times as its degree will allow. So a quadratic can cross up to 2 times. A cubic can cross up to 3 times. A quartic up to 4 times, and so on. The x-axis. And then turning points. A turning point is what we call when kind of you have a maximum or a minimum. So this one, I would go, turning point, there's one. Another turning point, another turning point. This is a quartic. The most turning points it can have is 3. A polynomial, whatever its degree is, the most turning points it can have is 1 less. How about a quadratic? How many times can it turn? Once. 1 turn. That's all it's got. Okay, on the back side, it asks for, I don't know if it asks for degree. Nope, just x-intercepts and turning points. Okay. So the blue is just extra information. It asks for zeros and turning points. Since the degree is 3, it can have 3 zeros, roots, solutions, x-intercepts. Only 2 turning points. A max of 2. Here's the degree, turning points, 1 less. Quadratic, the degree is 2. It can cross the x-axis twice. It can only turn once. Linear, the degree is 1. How many times can it cross the x-axis? Once. How many times can it turn? Is this a trick question? It's linear. It doesn't turn. That's right. Its degree is 1, so turning points would be 0. And last one here, the degree is 4. So it can cross the x-axis up to 4 times, and it can have as many as 3 turning points. Okay. Example 4, these are fun. I like these. According to the picture, state all the zeros. Okay, so I did that. -2, 1, and 3. Look how I wrote them. Then give a possible factorization. Well, if this is a 0, the factor had to look like this. This 0 and this factor go together. I know you know that. You don't often work problems backwards like that. I know. You're used to factoring it, then getting the zero. Well, now I'm asking you to just think backwards. If this is the zero, what would the factor have been? If this is the zero, what would the factor have been? So, back to where we were. Okay, got the zeros listed. Here's the pink factor that goes along with it. Here's the factor, here's the factor. And then I need to think about what my exponents on each factor might be. So, because of the fact that at -2 it only touches, my multiplicity had to be even. So it could be 2 or 4 or 6 or 8, and it said use the smallest possible. Okay, well, we'll go with 2. At 1, the graph crosses. So my exponent, my multiplicity could be 1 or 3 or 5. Use the lowest one, we'll go with 1. And the same thinking here, 1. Oh, and it said, leave it in factored form. Leave it factored, do not multiply it out. You're welcome. Here, however, it says multiply it out. It says write a possible equation in polynomial form. That's all right. Zeros are 0 and 5. Look how I wrote them. Turn those zeros into factors. Okay. It asks for an equation, so we need to put y equals in front of it. Now this is silly, okay, so I simplified this. That's silly, don't leave it like that. Simplify it to here. And then you can't leave it in factored form. It says put it in polynomial form. So distribute, see, polynomial. Okay. My zeros, and I've got these highlighted in yellow, are 4, -3. Oh, 4 and it occurs once, -3 and it occurs twice. So I went ahead and wrote it twice. So I turned this 0 into a factor, this 0 into a factor, and this 0 into a factor. This is factored form. It said, write it in polynomial form. So here's what you're going to have to do, and it was a little time consuming. I went ahead and multiplied these two out just because they're the same and they're kind of easy to FOIL in my head. So I FOILed in my head, first, outer, inner, last. And I took the result from these two and multiplied it by this one. So like literally, I sit here, let's see, that. No, I did it this way. No, I did it this way. Sorry. Put my finger on the x. I multiplied this times x squared and wrote it down. I multiplied this times 6x and wrote it down. I multiplied this times 9 and wrote it down. And then I looked at my finger and I worked on the -4 and I distributed the -4 to here, and to here. And then I collected like terms. A cubic, there it is in polynomial form. Oh, and then we have intermediate value theorem. This is kind of cool. Let me explain in teacher mode what all those words there say. Okay. Do you all agree that this point right here, it looks like it might be like, I don't know, -1 point something, comma 0. This is an x-intercept, a root, a solution, a 0. Okay, so look at this ordered pair right here. Do you see how the y value that goes with this ordered pair is negative? Check out this one. Do you see how the y value that goes with this ordered pair is positive? So an x value just to the left produced a negative y value. An x value just to the left of my 0. An x value just to the left of my root produced a negative y value. That means my function was below the x-axis right then. Got a negative y value. It was below the x-axis. Here, my function touched the x-axis. What happened over here? If I pick an x just to the right of my root, look what it produces. Look what this x value produces in my function. It produces a positive y. So if this x value produces a negative y, and this x value produces a positive y, do you know what y had to be somewhere along the way? How do you get from negative numbers to positive numbers? You have to go through 0. So what this is saying is this somewhere there was an x value that was a root. And I know this because my y had to be 0. How do I know my y had to be 0? Because my y's on the function, my y's went from negative numbers to positive numbers. So between when y was negative and when y was positive, y had to be 0. Where did it happen? Well, I don't know, negative 1 point something, right? This is like negative 1 point. But do you know for sure, though, that it was between negative 1 and negative 2? Yeah, you do, because negative 2 produced a y value of negative. Negative 1 as an x produced a positive y value. So I know my root is an x value somewhere between these two numbers. So here's what this says. You've got a cubic, okay? I think it's probably going to cross the x-axis somewhere, but I don't know where. It's a cubic. I wonder if it crosses the x-axis somewhere between x equals 0 and x equals 1. Let's find out. So, plug 0 into your cubic, you get a y value of positive 17. Now think about where that function is. Think about it. On a graph, right? You visual people, anybody there with me? Visual people. When x is 0, y is 17. So my function is above the x-axis. Above the x-axis. Okay? Now, move over one spot to the right. Just one. Move over one spot to the right. What's your y value? Negative 7. Holy moly. I went from positive 17 when x was 0 to negative 7 when x was 1. Do you think your function crossed the x-axis in between there? Heck yeah, it did. It went from positive x's to negative x's. Sorry. It went from positive y's to negative y's. So, talking x values, my root, my 0, my solution, my x-intercept had to be somewhere between x equals 0 and x equals 1. So that's how I answered the question. Yes, since the y's switched from positive 17 to negative 7, there's a 0, a root, a solution, an x-intercept between here and here. Let's try the next one. How about, does it cross between positive 1 and positive 2? Well, when x is 1, picture it, when x is positive 1, my y is negative 7. I'm thinking positive 1, I'm thinking quadrant 4. You thinking quadrant 4? When x is 2, so 1, 2, my y is negative 21. Oh, it's even down farther. So it started out like 7 below the x-axis. It ended up 21 below the x-axis. Do you think it crossed the x-axis? I mean, it could have. It could have like snuck up and crossed and then went back down to negative 21, but I don't know that it did for sure. So I'm not sure. The y values stayed negative. They didn't switch from positive to negative or negative to positive. They stayed negative. I can't tell if there's a 0. The intermediate value theorem is really cool if the answer is yes. If the answer is not yes, you're just like, I don't know. But if the answer is yes, if you switch from positive y's to negative y's or negative y's to positive y's, it's really cool. Like you can guarantee, yes, it had to have crossed. Yeah, there has to be a root in here somewhere because y had to be 0 in order to pass from positive numbers to negative numbers.